All right, so far we have been discussing a normal distribution, and let's talk about another type of distribution which is called log normal distribution. So a normal distribution, as we saw, basically looks something like this. It's normally distributed across its mean, median, and mode. And on the other hand, a log normal distribution is mainly used to model asset prices because they're always zero and above, always greater than zero. The asset prices will always be positive. So they're either zero or above. And for such a kind of a distribution, what we mean by the log normal distribution is if you plot on, let's say, if you plot the natural log, so instead of plotting, let's say you have the variable y, okay, so we have a random variable y, which can take on these different values. And y-axis plots the frequency or the probability of those values. Here, what we actually do is we take the natural log of y. Okay, so instead of taking the y, we take the natural log of y value. So if you have stock prices, you might take the natural log of $50. If it's on one day, it's $50, then it's 51. You'll take the natural log of 51. You don't need to know any numbers here. You just need to know about what log normal distribution mainly is. And when you take the natural log of y, as you see, and if it follows, if the natural log of y actually follows a normal distribution, then it is called a log normal distribution. I repeat again. So if the natural log of y is normally distributed, then it's called log normal distribution. All right, so that's what log normal distribution actually is, and mainly it's used to model a kind of a distribution or a kind of a data that is always positive and that will never be negative. And because of this reason, here is how the log normal distribution in its natural form would actually look like. Because it's bounded by zero, it will never go below zero, and it's skewed to the right side. That's how it would actually be. You see, it's positively skewed. Log normal distribution will actually be positively skewed. So a related point that we need to know that will lead us to the next topic is if a stock has continuously compounded returns, okay? So if a stock has continuously compounded returns and those returns are actually normally distributed, okay? So if this is how the continuously compounded returns are distributed for a stock, this is continuously compounded distribution, then this can actually be used if the continuously compounded rate of return is normally distributed, then by default, the future price of this stock or the future stock price will be log normally distributed. All right, so if the returns are continuously compounded and they are normally distributed, then the future price or the future stock price would actually be log normally distributed. And let us see some calculation for this. So let's look at a simple example where we say, if the stock price today is $100, and you expect that the stock price by the end of the year will become 108, so you are asked to find, so you have to find holding period return and continuously compounded rate of return. All right, so let's call this CPR, and let's call holding return as holding period return as HPR. So to find our HPR, holding period return, which is simply calculated as percentage change over a period of time or percentage return over a period of time. In this context, because there is no dividend, holding period return will be actually calculated as ending value minus beginning value, which will give you the price change. If there was dividend, you would have to add any dividend divided by the beginning value, which will be 108 minus 100 divided by 100. is equal to 8%. Alternatively, you can also find HPR using this formula, ending over beginning minus 1. And here's what we will do. We'll say 108 divided by 100. What that means is 108 divided by 100 gives you 1.08. So if you had invested $1, it will become 1.08. You simply subtract 1, and that gives you 8%. This is your HPR, or your holding period return. How do we find the continuously compounded rate of return? So we find that using this expression, which is the continuously compounded return, let's say CCR equals the natural log of 1 plus HPR. Let us see how we would actually get this. If we take the natural log of 1 plus HPR is 0.08, the way you would enter this in your calculator is you would first press 1.08. All right, well, how you will do this, you'll press 1.08, then you'll press second. Sorry, no need to press second. You will just simply press the natural log button, which is ln, just to the left of key 7, to the left of 7. So just press ln. And when you press that, the result you will get is 7.69%. Well, what that means is if you invest $100 today and that $100 grows continuously at a rate of 7.69% for a year, your stock price will actually become $108. All right, so that's how you will do it. Alternatively, you can also find the CCR as natural log of ending over beginning. It's just like, it's the same as this one, what you see here. So if you do natural log of 108 divided by 100, you should get basically the same answer. I would prefer that you actually use this. Now, most likely you could also get a question something like this. Let's say we're told, say continuously compounded rate of return is 10%, find HPR, find holding period rate of return. Now, this is where you need to know how to actually use your calculator properly. Firstly, you need to know one thing. Just like we know some basic idea here, if you want to remove a square, so let's say if we have this square and you want to remove it, you take the square root and this cancels out. In the same way, if you have a natural log and you want to cancel it, then you will use the exponential function. So the exponential function will actually cancel the natural log. So keep that in your mind, and let us see this now. So we know the formula CCR equals natural log of 1 plus HPR. If I apply this function, we say CCR is 10%, which means 0.1, 10% equals natural log of 1 plus HPR is unknown variable X. Now, for us to solve this, we need to remove natural log. So we'll have to take the exponential on both sides. If we do that, we take the exponential on this side, and on this side, this cancels. And here's what we have now. We have e to the power of 0.1 should equal 1 plus X. And how would you put this in the calculator? You will press 0.1 and then second and ln. If you do that, you get 1.105 equals 1 plus X. If we solve for X, X is equal to 10.51%. That's your holding period rate of return. That's how you'll find your HPR. All right, so we come to our last topic, which is Monte Carlo simulation. So in the investment world, Monte Carlo simulation is mainly used to study the risk of investments. And it actually involves a computer-based technique in which probability distributions play a key role. So the way it actually works is there are certain steps that you tend to follow in order to come up with a distribution of outcomes that would allow you to actually study the risk in a more appropriate way. So as a first step, what you do is simulation can be used to estimate a distribution of derivative prices or of NPVs, or of the net present values. So what I might want to do, for example, is let's say I'm an analyst, and I am studying, I'm looking at the financial feasibility of a hotel. So in order to see what should be the value of this hotel. So one way to value is you look at the present value of future cash flows. So you need to estimate the future cash flows and come up with the net present value of this particular investment. Now, what you as an analyst will do is, in order to estimate the value of the hotel, you will have to or the net present value of this particular project, you'll have to make a lot of assumptions, such as you'll have to assume what is the room rental rate per night. Let's say you're calculating the total revenue for the project. To calculate that, you'll have to assume what is room rental rate per night. You'll have to assume the growth rate in the room rental rate per night. You will also have to make an assumption concerning the occupancy rate. What I'm trying to say is you'll have to make a lot of assumptions, and based on these assumptions, you will actually come up with the overall net present value. So based on estimates for each of these assumptions, you will come up with the NPV for the project. However, of course, your estimates could go very wrong, right? Your estimates concerning room rental rate per night, the growth rate, the occupancy rate could be very wrong. And that's why you will run a Monte Carlo simulation to try and study the impact of these changing on the NPV. So first you will specify what you actually need. You want the NPV of this, let's say, hotel. Second step would be the specified distribution of random variables. What are the random variables? In our case, the random variables could be room rental rate per night. We don't know what will it exactly be. The growth rate in the room rental rate per night. Again, we don't know what will this exactly be in the future. And the occupancy rate, for example. So you specify them. We have already specified. And what we're looking for is the NPV. Third is you let the computer randomly generate different values for each of these. Keep in mind one thing, when you're specifying distribution, you'll have a full distribution of room rental rate per night, and you have to make an assumption. Is this normally distributed? What kind of distribution is this? What about the distribution of growth rate? Is that normally distributed or not? So that will be your second step. Third step will be you'll use the computer to generate random values for each of these random variables. And when it generates random values, based on that, it will value the hotel, or it will basically use this step to come up with the net present value once. And then all these steps would again be repeated. So the second step and third step would again be repeated thousands of times, meaning the computer will randomly generate a value for each of these random variables once, get the NPV, then randomly generate again, and then get the NPV, and it will repeat that thousands of times. The more trials you do, the more accurate it would actually be. And then once you do that, now you will have now you'll have a full distribution of NPVs, right? Which mostly, if you've run a lot of trials, you'll find something like this. Most of your NPVs that were calculated or computed using the simulation program, you will have a mean NPV right here, and most of them will be centered around the mean. So now you'll have the mean of the NPV, and you will also have the deviation and the variance of the NPV. Now, one limitation with Monte Carlo simulation is that if you're using random generation of the random variables, if you're using random values, the results or the random values might be very wrong or could be absurd. And for that reason, we have another type of simulation, which is called historical simulation. The only difference between Monte Carlo simulation and historical simulation is that it generates random values from distributions of historical data. So unlike before, where we had a random distribution of, you will have random values for each of these, right? The computer randomly generates value for each of the random variables. Unlike this, in the historical simulation, we will have a historical distribution for each of these random variables. So for room rental rate per night, you will have a historical data, for growth rate as well, as well as for occupancy rate, you'll have historical data, and the computer will randomly generate the values from the historical data. So that will be the pool, or that will be the input into the computer program. The advantage is you don't have to estimate the distribution of risk factors. So you don't need to estimate the room rental rate per night, growth rate, if you're using historical values that you have actually got. But the disadvantage is, if let's suppose you have come up with these room rental rate per night, growth rate, or occupancy rate on the basis of historical period, in which in that historical period there was never ever a crisis. For example, you came up with these inputs on the basis of a data from 2010 to 2015, and we know that between 2010 and 2015 there was no market crash. So because of such historical data, your computer will not be able to simulate outcomes outside of that historical data. So it will never be able to estimate that because of a market crash, the room rental rate per night might actually crash down to a very significantly low value. So that is one limitation. So future outcomes for risk factors may be outside the historical range. As we said, if a particular security only came into existence after 2010, we do not have observations for its behavior during a market crash, and hence you will not be able to simulate how this security would actually perform during the market crash. And with this, we are done with the rating.